we have the opportunity to learn about virtual allowable generation. It's going to be virtual allowable, being effect of defects, modeling of continuous fiber reinforcement. Today, my presenter is going to Dr. Anthony Jett. He is the business development engineer for aerospace at e-Xstream Engineering, part of Hexagon Manufacturing Intelligence. And he has almost 20 years of experience with different FEA software. And then today, he's also very actively working in the aerospace industry with our solutions. So hi, Anthony. Can you hear me? Are you here with us?
Yes, hello, Mira. Yeah, I'm here. I can hear you well.
Super. So before I'm passing the control over to Anthony, just for your information, we are going to answer your questions at the end of this presentation. And in the meantime, you are very welcome to type in your questions, either in a Q&A or in the chat window, and we will answer all of them after the session. And the webinar is recorded, and the recording is going to be available on demand after the session once it's ready. So, Anthony, if you are ready, then I will pass the control over to you. And I wish for everybody a great presentation. Enjoy your webinar. I confirm your screen, Anthony. Go ahead.
Okay, so thank you, Mira. And hello, everybody. So, like Mira explained, my name is Anthony Chervet. I'm the business developer for aeronautics at e-Xstream Engineering, and I will have the pleasure to show you how we handle virtual allowable generation, including the effect of defect based on an advanced failure modeling for continuous fiber reinforced polymer. Oops. So, a brief overview of the presentation of today. So, I will first start with an introduction and expose what are the challenges in terms of composite material modeling when we want to address the generation of allowables. And then we'll see a bit in detail the new features that have been developed in DigiMat to address those virtual allowable generations. So those two new features are related to a new advanced failure model that I will take some time to expose you. And I will also emphasize on some additional capability that we have had, which concern the possibility to model defect in the coupon. And then we'll do summary conclusion. So quickly, before we go into the detail, a brief introduction about e-Xstream Engineering. So if you may not know well our company, so we are e-Xstream Engineering. We are people who work mainly on material and process simulation. We develop a platform which is called DigiMat, so that supports all our development in terms of material and process modeling. We are also in charge of a platform which aims to manage the material data lifecycle. So this platform is Material Cell, and we belong since 2012 to the MSC Software company. MSC Software company is a part also now of Hexagon, which is the mother company who propose solutions to connect physical and digital world. At e-Xstream Engineering, we have also developed an integrated computational material engineering strategy, which has been articulated around 10 axes. So I won't go into the detail of those axes, but you could see that this strategy aims to address everything related to material or virtual material development, to virtual material testing, but also to everything concerning the material data lifecycle management, material exchange, to aim or to facilitate the communication between material supplier, material user, also possibility now to verify the compliance and sustainability of the material that you want to use. We also emphasize our capability to take into account the effect of processing, to propose accurate material modeling, and also, as you may know, we have our complete solution dedicated for the simulation of the additive manufacturing process. Additional way of development that we are active recently try to propose methodology for material intelligence and using hexagon capability, working in the digital continuity. But today, like I explained in the introduction, we are going to focus on this second axis of the strategy, which concerns the virtual material testing. So let's start with a summary or a presentation of the challenge concerning the composite material modeling. That will be short. So we know that when we do the insertion of composite material in a new design, we have to follow what we call the building block approach. So the building block approach, it's aimed to verify or to verify the how to say to verify the correct choice of the material at every level of that pyramid. So the first level of this pyramid concerns all the work that has to be done at the coupon level, from material screening, material specification development, and generation of the allowable. And since we have introduced composite material into the design, the size of this first level, by the need of comparing and screening different configuration in terms of layup, in terms of coupon configuration, in terms of environment condition, make that this first level of the pyramid become extremely time-consuming and require a very large experimental test matrix. So we try to propose, one of the challenges here at this level is to try to decrease a bit the workload associated with all this work at that level. And that's why we come with a solution, so Digimat VA, that aim to propose a virtual testing solution to predict the laminate strength or to predict the allowable. So we have that solution, which is now Digimat VA. It's a productive tool that will help the user to define, to solve, and to post-process a complete test matrix for some specific ISTM standard test in order to determine the allowable of the coupon. So once we have developed this, when we started to develop this platform, we had to tackle a series of challenges. And the first challenge is obviously to be able to predict an accurate prediction of the failure of the coupon. And at the opposite of a metallic material, which exhibit a very clear modification in its behavior, like a non-linear yielding, for composite, the only reliable and observable event is the final failure. And most of the time, and what is considered as the allowable, it's the final stress or the final strain. And when we load a coupon like this, we can observe a very brittle failure, but between the moment we start to load the coupon up to the final failure, some critical events take place on the coupon, such as initiation of the matrix cracking, initiation of the fiber breaking. And if we want to be able to predict the final failure, then we have also to be able to, we have to use a numerical model that is able to predict all the critical events that take place prior or before the final failure. So that's the first challenge. It's to develop or to use a material model that will be able to predict properly all the critical events that take place in the composite or in the coupon before the final failure. Then we have another problem or another challenge when we use composite material. So if I replicate 5 times, 10 times the coupon that I've just used before, I will never get 10 times exactly the same final strength. So at the difference with metallic material, what we observe with composite, it's a larger distribution of the final strength. So this means that, or this raised the need to use what we call the allowable material, which would be a material property that is statistically derived from test data coming from a stable process. And this value, which will be used for the design, must be a value of confidence. So that's why we generate, or we give the possibility to generate a B-basis value to take into account this distribution of final strength of the couple. That's the second challenge. If we want to be able to predict a distribution of results like this as we observe experimentally, then we need to have the possibility to define a test matrix that will allow us to capture the variability that is expected during the production and during the life, I would say, of the coupon, and variability that can come from several sources. So we give the possibility in DigiMat VA to define a test matrix. So we follow recommendation coming from the FAA, and this test matrix will allow us to introduce variability at the material level, at the process level, let's say at the generation of the panel, and also variability of what we call the post-process variability. So it's the variability that can come from simply the way we will test the coupon. But that's the second challenge. It's the possibility to have or to insert some variability during the generation of the coupon strengths. A last challenge, it's the possibility to take into account the effect of defect when we compute the allowables. So we know that there is defects that appears in the composite material during the manufacturing process. We have several types of defects, such as porosity, waviness, or fiber breaking, and those type of defects take place or appear no matter the type of manufacturing process that we are using. Porosity can be many times associated with RTM process or autoclave. Thermoforming can lead to waviness or fiber breaking. Automatic fiber placement can lead to presence of the gap in the coupon. So no matter the manufacturing process, we know that there is some defect in the composite. And we know that the sizing of the composite part, or let's say the value that we use for the sizing, should take into account the presence of those defects that come from the manufacturing process. And each defect will affect the mechanical property, and which depends on the type of the defect, the size of the defect, and the location on the coupon. So that's why we have a third challenge, which is that we need to have a numerical tool that allows us to study the effect of defect in order to help the refinement of the determination of the knockdown factor that is applied on the coupon strength due to the presence of defect. That we will see in detail during that webinar, how we handle those third challenges. So we have put all those capabilities, all this knowledge in that platform DigiMat VA, which is our platform to compute virtual allowable. So on this slide, I have given an overview of what is DigiMat VA. It's a platform that will allow you to have a very efficient framework to automate the test matrix generation and to execute your test matrix. We'll see in detail how we handle that. And then once you have defined the test matrix, you can post-process and you can manage the resolution of the coupon. In DigiMat VA, we have also proposed a connection to Material Center. Material Center, it's our material data manager. And then in DigiMat VA, we propose also several levels of fidelity in terms of failure model. So we have some tools which are based on the classical laminate theory and associated with the first life failure. So that's not something I'm going to show today. We have also a first implementation of our failure model, which is what I call here the quick failure model, so which corresponds to what we implemented when we created that platform, so let's say 4 years ago. And we have that new advanced failure model, which is based on an academic state-of-the-art, which is something that I'm going to show you in detail right now. Third main capabilities in DigiMat VA is the possibility to insert some defect to evaluate the effect of those defects. So three types of defects are covered now in the platform: the auto-apply waviness, the porosity, and the gap coming from the automatic fiber placement. And then, like I mentioned, when I listed the challenge, we have also the possibility in Digimat VA to address the variability and the uncertainties quantification. So we propose capability to run parametric analysis. So that's not really variability, but it's just a discrete distribution or discrete value that can be defined here. And we have also those constituent, we can also address the variability at the composite constituent level and on the fiber volume fraction using a Monte Carlo approach. Also, ongoing development, it's the possibility to have uncertainties quantification, but this time on the effect of defect. So that's not something I will go into the detail today. We did already in the past some webinar on those capabilities, but if you are interested, this is something we can still arrange another meeting to address this fourth capability. Today, we will focus mainly on this new advanced failure model and the possibility to have effect of defect. So let's go into detail of this new advanced failure model, which is available since the last version of Digimat. So if we just think about the need or what we need when we define an advanced failure model, so this model should be able to predict the critical event prior the final failure. So that's what we have seen is the first challenge. But also, as we know, when we deal with damage, when we deal with finite element simulation, we'll have some challenge coming from what we call the damage localization. So an accurate failure model should have capabilities to limit the mesh sensitivity and the damage localization. And also, last thing, it's damage or a material model should be easy to use and should rely on measurable parameters. So some parameters that we know how to identify those parameters and we know how to use that, or we understand their meaning to the numerical model. Also, to address material variability, the numerical model must be expressed in terms of constituent property and fiber volume fraction. So to answer those needs or those challenges, what we have done is we have implemented a state-of-the-art academic framework, which has been proposed by Professor Kamano. So we started from collaboration with Professor Kamano, and we base our work on those three references. Well, there is more references. Those one are really the one who proposed the foundation of this numerical model. And this one has been implemented in Digimat 2019.1. So if we look into the detail in the key ingredient of this numerical model, so the first point of this numerical model is that we use an elastoplastic behavior coming from the resin. And the way this elastoplastic behavior of the resin is identified, it's extracted from the from the in-plane shear curve of the lamina. So knowing the in-plane shear curves of the lamina, we are going to extract the elastoplastic behavior of the resin. Second ingredient of the numerical model, we use LARCO 3 as a damage initiation criteria. So LARCO 3, it's already something well established in the community, let's say, and it's a failure criteria that allow to predict for intralaminar failure mechanism. This LARCO 3 has also something which is extremely interesting, is that it takes into account the rotation of the fiber due to the misalignment in axial compression. So if we see that into the details, so when we are in axial compression, so the model will consider that under axial compression loading, the ply will fail due to fiber kinking, where the resin in the vicinity of the local misalignment of the fiber will fail in compression. So this is what is represented here on that scan, we have here a misalignment that appears, and in the vicinity of this misalignment, the matrix will fail in compression. So in the failure model, the failure model proposes a methodology to compute this angle of misalignment. So this is what is noted phi here, which is based on material property or laminar property. You see that here we use the XC to compute the misalignment angle. Compute also what we call longitudinal friction coefficient, which also rely on material parameters. So once the misalignment angle has been computed, then the stress can be rotated into the misalignment, into the frame that represents, or into the misalignment frame, and the failure criteria can be computed using those rotated stresses. For transverse tension and transverse compression, we always have a combination of the transverse stress, sigma 2, and the combination with the in-plane shear stress. So that's the case for the transverse tension, the case also for the transverse compression. So once we have defined and computed the damage initiation criteria, we need to propagate the damage. So we need some damage propagation law, and in this case, we have coded the damage propagation law proposed directly by Professor Camano. So that's what it's called here, University of Porto damage model. And this damage model includes the crack closure. So the damage initiation threshold are related to damage variable by the damage evolution law. So that's the damage initiation threshold, it's LARCO 3, and then damage evolution law are the one proposed by University of Porto. And we have that possibility to take into account the crack closure when we are going to reverse the loading. So typically, if a crack is created under tensile loads, it will close up under compressive load, and the material will recover part of its load carrying capability. So that's why we see here that we have the propagation law R1 minus, which depends only on the compressive condition. But at the opposite, a crack created under compressive load will remain open under tensile load. So that's why here we have R1 plus, which depend not only upon the failure area in tension, but also once we have seen some compressive load prior the loading condition or the tension condition. So the way those propagation laws are defined, they have a specific shape. So they are linear and bilinear softening damage evolution law. So this is the typical shape that we use, so bilinear and linear, so depending on the loading condition. And those evolution laws are associated with a crack band model. So here, the propagation law here is a function of a physical parameter. So those propagation laws are defined function of the intralaminar fracture toughness to correctly reproduce the energy dissipation during the propagation of the damage. But those propagation laws are also function of the characteristic length of the finite element to decrease the mesh size sensitivity, making sure that we have the same energy, the same quantity of energy dissipated per unit area of crack propagation, no matter the size of the element. So typically that's the crack band model. It means that the area under the propagation law is connected in some way to the area or to the volume of the finite element. And once we have degrade the stiffness of a finite element, we make sure that the quantity of energy that is dissipated is not function of the size of this finite element. So it means that if we have this if you see my mouse, if we have one specific shape of the finite element for specific volume, sorry, then we are going to dissipate a specific quantity of energy. But if this finite element is, let's say, 2 times smaller, then we'll make sure that the energy that will be dissipated is 2 times bigger. So it means that at the end, the quantity of energy that is dissipated is the same. And that's the methodology, the method allow to decrease, in this case, the mesh sensitivity. Another features of this model concern the delamination. So in this case, delamination is handled using cohesive zone model, cohesive zone element. So it's based on cohesive element, and we use the Bent-Sega energy-based criterion to predict the delamination under mixed mode loading conditions. So here, what we have coded, it's simply the framework that has been proposed by Professor Turon from Gijón University in Spain. The model handles also the in situ strength. So the in situ strength, it's a modification of the strength of the ply, so only the strength that is governed by the matrix, so the wild C and the in-plane shear. So it's a modification of those 3 strengths value based on the localization of the ply in the laminate. And then the last features correspond to the possibility to take into account manufacturing stresses. So this, it's a feature that we added to take into account stresses or residual stresses coming from the curing cycle. So it means that before we load the coupon mechanically, then we apply a thermomechanical load from the curing temperature to the room temperature in order to introduce some residual stresses in the coupon before the mechanical loading. And this is done now systematically once we use this advanced failure model. So at the end, we end up with a list of data or a list of material parameters. So typically we have here the laminar data. So we found the stiffness and strength, axial, transverse, tension, compression. So I would say this is some data, typical data that we can find in the datasheet. And we need some additional parameters to handle the damage propagation loss, what we call here the fracture toughness in the ply, so intra-ply fracture toughness for the 5 modes, so axial, transverse, tension, compression. We need also the coefficient of thermal expansion, so of the ply, so the axial and the transverse. So this is for to take into account the residual stress coming from the manufacturing. And then we need also the interface data. So interface data, it's the fracture toughness in mode 1, in mode 2, the nominal or the damage initiation stress in mode 1 and in mode 2. So this advanced failure model has been implemented in our platform, so Digimat VA. So for those who don't know, so Digimat VA, it's proposed an extremely simple workflow to define and to set up and to solve a test matrix. And the workflow follows different steps, specific steps, very straightforward workflow. First, we have to define the material data. So this is the material parameter that I've just listed that needs to be entered in the software. And then the user has to define the layup. So here, quite straightforward. We can define any type of layup. And then we have to define the test geometry. So test geometry, we propose a library of tests, which are all parameterized. So the user can really define the configuration that he has really, that he would like to test. So after that, we have the possibility to insert the variability, but like I explained, I won't go into the detail of the variability today. The variability is an option. We don't have to always study or integrate the variability. So let's assume that we don't have variability here. So once material data, layup, and test configuration has been defined, we can go for the resolution. So it means that here Digimat VA will create finite element model corresponding to each configuration and is going to solve this finite element problem. So solve the finite element problem, it means that we are going to extract the stress strain curve, and we will consider that the allowable is the maximum of the stress strain curve. After this, we do post-processing. So post-processing, it means if we have defined variability, then we will be able to extract, for example, a mean value over all the configuration or a b-basis. If we don't have defined the variability, then we will have a single value which will correspond simply to the single strength value or single maximum of the stress strain curve. So this is, for example, how the parameterization of the coupon is handled in the platform. So you see that I will do a demo right after, but during the workflow, the user has to select the type of coupon he wants to insert in the test matrix. So there is, we cover, for example, the n-notch configuration, the open hole, the fill hole, and we have also as a configuration I will show on the slide after. But each coupon has been parameterized, and the user can define, really set all the dimensions that he wants. So for the coupon who have, for example, a fastener, like the fill hole and the bearing test, we have also parameterized the fastener configuration or the geometry, and the user can define between different types of fasteners, so countersunk, protrusion, and define the properties. This is the test, all the tests that are covered in the platform. So from n-notch test, open hole test, tension compression, the fill hole, again, different geometry of the bolt, the bearing test, single shear bearing, double shear bearing with one bolt or two bolts, and also the V-notch rail test. Okay, so at this point, I will do a demo just to make sure everybody is clear with the platform. So when you open Digimat, you have this first landing page. So what we are going to do is we're going to open Digimat VA. And then I will create a new project. So here you have the data tree, which give, or the data tree, which will give the workflow, all the steps of the workflow. So the first step is to create a material. So I will select one material here. Let's say I will take this IM78552, which is noted here underscore LM, which means last model. So this is the name I choose to define the IM78552. Then I can define all the layups. So you can define some pre-defined layups, save it in the database to reuse easier for different usage. So here I will select a quasi-isotropic layup, and then at this point you can select the type of coupon that you want to test. So I will choose, for example, an open hole. So you see that if we go back, we can change the unit system, and you can set different dimensions for the coupon. So I would select an open hole, and I can select also a non-notch intention. So again, you can set all the data that you like. And then we define also the environment. So here, next step, is we define if we want to insert variability, or if we don't want variability, or if we want a parametric study or a defect study. So for the moment, I will just choose no variability, and I will continue the workflow. And then here we arrive at the material model step. So here you see that this material has been used in two configurations, the open hole and the n-notch that I have defined. But if I click here, we have, for one material, we have two different fidelities. So you have the standard PFA and you have the advanced progressive failure analysis. So for this demo, I will choose the advanced one, and I will do the same for the second one. So now I have selected the advanced one. I can open it. So by clicking on this icon, I can open the material tab. And this is all the data that the user here has to define. So the ply property, stiffness and strength, axial, transverse, tension, compression. And the user needs to define also the coefficient of thermal expansion in the axial and in the transverse direction. And then we need also to define some properties. So the matrix property, the condition of the testing condition, and we need also to give the axial value of the coefficient of thermal expansion of the fiber. So this value is quite easy to find in the fiber datasheet, for example. So we do a calibration here. So when we say we do a calibration, it means that based on the laminar data and information we gave at the matrix level and the CT of the fiber, we are going to identify a bit more in detail the matrix property and the fiber property. And those can be used if we go for the variability analysis at the constituent level. That's what we are going to use. And then another additional parameter now needs to be defined. So those parameters are related to the damage propagation law, and that's where the user will have to define the intralaminar fracture toughness, so in axial tension, in axial compression, in plane shear tension, in plane shear compression, and in plane shear. Sorry, in plane tension, in plane compression, and in plane shear. So then the last thing that we need to define is the interface property for the delamination. So like I explained, we need the fracture toughness in mode 1, in mode 2, the delamination stress or the damage initiation stress in mode 1 and in mode 2. So once we have defined those material parameters, then we need to define the mesh settings. So we have put in the software some default parameters that can be used directly with this advanced failure model. So if I switch here to the advanced setting, I will click here on settings, and I have the possibility to create the mesh settings for the advanced failure model. That's what I'm doing here. And some data comes automatically. So this is the default value. And this is what we use for the moment, for example, for all the validation work that we have conducted. So one for the notch, and then I need to do the same for the open hole. So for the open hole, we can create the advanced model mesh settings, and they are created here. So what I need to do now, I need to affect or to apply those settings on my coupon. And then now I can generate the mesh. So I can visualize the mesh, so we can visualize the open hole tension mesh. And we can zoom a little bit around the hole. So we see here three colors of through the mesh. So this means that we have actually three different materials. This is due to the in situ strength of the composite. So we have three different materials. So here, because of the this one because of the symmetry, this one because it's an external ply, and those one it's nothing special. They are just inside the laminate. So the mesh settings are done in such a way that we respect some rules for the meshing. So we try to have square finite element here, and the default mesh settings are computed in such a way that we respect also a dimension that will ensure to have a correct description of the failure and the failure propagation. So that's what we have for the open hole, and that's what we have also for the unnotched coupon. Again, if we zoom, so we have a specific size to make sure that we are going to reproduce properly the failure And we have also different color. Again, this is due to the in situ strength and the position of the ply within the thickness of the laminate. So if we are at the symmetry plane, if we are external, or if we are inside the laminate. So once we have done this, then we are in the situation that we can execute the test matrix. So I will not do it because it takes quite a lot of time, so we don't have the time to run those coupons here. But just to mention here that it's possible to use parallel resolution, and so it's possible to use a remote solver. So if you have also installed Digimat VA on a cluster or on a HPC computer, then from your laptop you can execute or you can submit remotely the jobs on your machine. So if I can, what I can do is simply open a new session that contains some result, just to show you a bit the post-processing. So what I'm doing now is I'm loading a session that contains some result. So for something very similar to what I have defined. So here we recognize a test matrix. So for the post-processing, I can go directly in the allowable key, and then we can we have two levels of post-processing. We have what we call the global post-processing, which give the stress strain curve. So typically, each step you can visualize the stress strain curve. You can have information about the strain value that has been measured. You have also the possibility to do a local post-processing. So local post-processing will give you access to the post-processing of the detailed post-processing of the coupon inside the coupon. So typically you can visualize the damage variable. So the damage variable in the axial direction, damage variable transverse direction, and the damage variable in the interface, so the delamination. So to visualize the delamination, I need simply to select all interface, and then here we have, if I remove the first one, here we have the possibility to verify if delamination takes place in the coupon, the resolution. So this is for the demo. You see that it's a very quite easy workflow. It doesn't require too much time to be very comfortable with the platform. So once we have done execution of the test matrix, obviously we want to make sure that the failure model is accurate. So what I'm going to show here, it's probably, if there is one graph that you should keep in mind, is this graph. So this illustrates the validation work that we have done with this new failure model, and this has been done using the main aerospace grade. So you see that we have tested the T100 M21, the IM7-8552, the IS4-8552, and the IM7-97 with the 977-3 resin, and another composite that we cannot disclose the name. So those materials have been tested on the unnotched tension compression and the open hole tension compression. They all consider intermediate or high modulus with a high strength carbon fiber and an epoxy resin. And those has been also tested on several types of layup. So we have here some quasi-isotropic layup, some hard layup with 50% of ply oriented at 0 degree, some softer layup with 80% of the ply oriented at ±45, but also some non-traditional layup and some layup that present some ply bunching. So on this graph, what is represented, it's here you have on the x-axis, it's the measured strength, so the experimental value, and here on the ordinate, it's the predicted value, so the value computed by the model. And here in orange, you have that line, and if all the dots, all the predicted value are exactly the one that has been measured, it means that I will have all my dots positioned on this line. So here in the dashed line, you have the envelope plus minus %. So now for each material, each configuration, I just need to to position the measured strain. And then you see that now what we can easily see is that we have almost all the dots are located in the envelope plus and minus 10%, with some dots that are exactly located on this on the orange line. So we can identify, we can get that those points are the end-notch intention, and here those one the open hole in compression. So we have still some dots that are outside the plus minus 10%. Those one typically here and here. Those are mainly for the X4-8552 materials, and it's also mainly for the unnotched test in compression. So we have probably identified, let's say, a shortage in the LACO3, and we are working on the possibility to improve the prediction for the unnotched compression test. If we see some detail, so a lot of data here. So this is the detail for the IM7-8552. So here typically we use the data coming from the NIAR report from the count database. So, and we can localize where we don't have a good result. So like I explained, for the unnotched compression, we have only minus 15% of error. For the unnotched compression test with a soft layer. So that's the most challenging to simulate. And here you have the result for the T100 F21, so with quasi-isotropic layer, with laminate with bunching. So typically with the bunching is this type of laminate where we have 2 ply at 0 consequently. So, and then also the hole size effect. You have here some configuration where you have 3 dimensions of the hole. So all those one give really acceptable result. And so one thing that I have not mentioned so far is that all those tests, all those values, has been obtained with exactly the same configuration for the unnotched test. So all the unnotched tests here, no matter its tension and compression, has been run with the same mesh settings and the same solver setting. And that's the same for the open hole. All the configuration, tension, compression, has been run with the same mesh settings and the same solver setting. So it means that the mesh settings by default that I have shown just before, those one has been used and has not been changed from a configuration to another one. We don't need to change the mesh setting if we are dealing with a hard layup or soft layup. There's no this kind of rule. We just use the same mesh settings, no matter the layup and no matter the test. Okay, some other example also of validation. So here it's interesting work that we have done just to show the effect of manufacturing stresses, where we can show that it improves the accuracy and it will lower a little bit the coupon strength. So this is a work that has been done using the data coming from the IFRL benchmark that was proposed like maybe 3-4 years ago now on this type of material, so IM7-977-3. What is interesting here is, in addition, it uses some non-traditional layer where we have ply oriented at 30 and 60 degrees. So you have here the result that we have if we don't take into account the manufacturing stresses. And in this column, if you see my mouse, it's the result that we have if we take into account the manufacturing stresses. And we see that with those manufacturing stresses, so with the thermomechanical load step before the mechanical load step, we improve the accuracy, no matter the type of layer that we are using. So the accuracy is slightly improved when we take into account the manufacturing stresses. Okay, so let's move on now to the next part of this presentation, which is now the possibility to introduce or to couple this failure model with the effect of defect. So, like I explained, we have introduced in DGMAT 19.1 the possibility to insert a defect in a coupon, and I'd like to mention that this work related to the effect of defect is supported by a Clean Sky 2 project. So Clean Sky 2 project is CDESK, And it's done in collaboration with Airbus, which is here the topic leader. And we are working with two other partners, so Senairo, which is a research center in Belgium, and Sonaca, which is an aerospace tier one, also located in Belgium, and who develop some slat and leading edge of. So in this project, we are dealing with three types of defect. The first one is the porosity in the composite. The second one is the out-of-ply waviness, and the third one is the gap from automatic fiber placement. So the reason why we wanted to focus on the effect of the defect, it's because we had the objective at the origin to build a numerical tool to study the effect of defect in order to challenge the defect acceptance criteria for future aircraft part development. So the thing is, we have to see how it's done today. So when we have to deal with effect of defect in the current design process, we use a knockdown factor. So the knockdown factor, it's a coefficient that is applied to the allowable value obtained on a pristine configuration, and we obtain, by multiplying this knockdown factor to this allowable, we obtain the allowable with defect. But today, this knockdown factor has been identified, or the value of this knockdown factor has been identified based on regular inspection, and this value has been defined based on the severity, occurrence rate, detectability. So it's a bit an empirical way to determine this knockdown factor. So that's why we try to propose a numerical tool to refine the determination of this knockdown factor. So the first defect that we have to deal with is the out-of-ply waviness. And when we think about the waviness, we have to try to understand or to visualize what is the out-of-ply waviness in order to define properly the specification that the specification of the development. So if we check here, we see that when we have the waviness, so the fiber orientation must follow the waviness of each ply. We can also observe some large variation of the ply thickness due to the waviness. So it means that if we have variation of the ply thickness, we have a variation of the local fiber volume fraction, which probably will affect the local ply, so in terms of stiffness and strength. We have also probably apparition of the out-of-plane stresses that will contribute to the delamination, so especially in compression. And we see also that we can have several wavy areas over the coupon with different type of curvature. So that's why we gave the possibility. So this is a view of the tab where we define the defect in the software. And that's why we give the possibility now to come and superpose some waviness onto the coupon. So we have the possibility to define several areas of waviness over the coupon. We can position the waviness over the coupon. So here we are at the third one. The third one is this one in orange. You have the characteristic here of that waviness area, so the position, the wavelength, the orientation. So here it's a 0, but you can rotate slightly the waviness. And then we need to define the amplitude of this waviness. So we have different ways to define the amplitude of the waviness, from a very simple one to the most advanced one, which is the one that I show here. And in the most advanced one, we can define the amplitude of the wave ply by ply. So for each ply, we can enter the value of the amplitude of the waviness. And we can, like this, describe a very refined waviness. Then we can visualize here the profile of thickness through the laminate. So the idea of this development is to run the coupon with and without the defect. So without the defect is what is written here, the pristine one, and to extract the knockdown factor. So typically here I run a coupon. This is this defect. So we see here quite a severe amplitude waviness in the coupon. And then we can extract now the strength with the defect and the strength without the defect, and we can compute this knockdown factor. We can also do the post-processing and identify the failure mode, and we see that for some quite severe waviness, the main failure mode, it's mainly delamination and very few damage in the matrix here. The third defect that we can deal with, it's the porosity. So when we had to think about the way we want to define the porosity, we need to understand that the porosity, it's a surface information. So what is done typically in production, we have a technician, we have technician here which will have an ultrasound system and will try to detect the porosity through an attenuation of the signal. So what is done, it's we have some So what is done, it's we have that we measure the attenuation of the signal, and when the attenuation when different attenuation is identified over the surface, it means that we suspect the presence of porosity through the thickness. So we have only that information on the surface because we don't cut systematically the plate just to verify the level of porosity. So that's why we just know where the porosity is suspected to be through the thickness of the laminate. So when we detect an area like that with an attenuation of the ultrasound, then we give a kind of normalization of that area. So we, let's say, define a rectangle, and then it means that for all the material under this area, we consider that we have the presence of porosity. But we don't have any information on the distribution of this porosity through the thickness. Unless we cut again the plate, the coupon, we don't have any way to identify where this porosity is located through the thickness. So that's why we made the assumption in the software that all the ply under this surface is concerned by the porosity. So it's a way to remain conservative. So the way it's done in the software, so here again, the user when the user defines his coupon, he will have to define a specific area where he wants to study the effect of the porosity. So he can consider that the porosity is completely present all over the coupon, but it can be also in a limited area here, like on this orange rectangle. Then he has to define a porosity fraction, so let's say 3% or 5%. And then what is done behind the scene of the software, Digimat is going to compute the lamina property, but taking into account the porosity. So we are going to build a kind of multi-scale approach here. We go back at the lamina level, we insert some porosity, and we estimate the knockdown factor on the lamina property and interface property due to the presence of the porosity. So it means that when we are going to run this coupon, we will have two materials. We will have one material here in the red part, which is the pristine material, and we will have another material here under the orange part, which will be the material with this new property taking into account the porosity. And then we can run the coupon, and again with two types of material, and we can compare this time the pristine coupon and the coupon with porosity. So typically some results. So this is some result that we have for the ply when we have introduced 5% of porosity. So this is the first step of the workflow. First, the ply property in presence of porosity, and then we will solve the coupon, so the pristine coupon without porosity, and the coupon with the porosity, and again, we identify the knockdown factor. Okay, so the last defect, it's the gap coming from the automatic fiber placement. So the automatic fiber placement, okay. So the automatic fiber placement, it's a very promising process, manufacturing process, where we have a robot that come and make the deposition of strip of unidirectional. And once we have to rotate the robots, or when we have to do the deposition on the double curve surface, some gap appears between those strips, and we want to take into account the effect of the presence of those gaps inside the coupon. So here what we do is we evaluate the knockdown factor on the flat coupon configuration due to the presence of the gap or due to the misalignment. So here, important to understand that the position of the gap and their characteristics, so it's mainly the size, are defined by the user directly in the user interface of Digimat VA. So this is again a view of the way we define the coupon on the laminate. So the user has to define first the toe and the courses characteristics, so the toe width and the number of toe per courses. And then there is the possibility after that to have a very refined way, a very refined definition of the position of this gap. So we can have, for each ply of the laminate, we can define different gap between the courses, and we can, so it means, for example, here for this ply at 45, I can ask to have a ply which is 1.5 millimeter width, but this ply at 0, I can ask to have a gap which is 2.5 millimeters. And I can do that for any ply in ply. So we can define the process parameters. We can visualize each ply. So this is what we visualize here. I have to view to see the layer 5. So the layer 5 is oriented at 45. That's what we see here. And we want a gap between the courses, which are 1.5 millimeters. So we can select the ply that is concerned by the gap, and we can have different gap values for different ply. And then we can also shift, or we can translate the gap with respect of the center of the coupon. So once the gap has been defined, they will be mapped onto the mesh. So it means that we have the gap. It's a geometrical definition, but we have the mesh. And the mesh is always the same. We don't change the mesh if we are dealing with gap. We are simply mapping the gap onto the mesh. And then, based on the location of the gap onto the mesh, we are going to refine the fiber volume fraction based on what we call the percentage of coverage. So if you have, for example, gap one element, then we won't modify the fiber volume fraction. If you have a gap that is just at the limit of, if you have some element which is just at the limit between the gap and where there is no gap, then we will adapt the fiber volume fraction based on its location with respect of the position of the gap. All the elements which are exactly in the middle of the gap, for example, will have a very low fiber volume fraction. So they will have the resin property in this case. And this adaptation of the material property is done using the mean field homogenization. So again, based on the position of the element with respect of the gap, we are going to modify the material property to take into account the fact that one element can be exactly in the middle of the gap, one element can be at the limit of the gap and the composite or the ply. So here you have an illustration on the evolution of the ply strength with the fiber volume fraction, so using the mean field homogenization. So from this is from 60% of fiber to the pure resin, and you see the evolution of the axial strength, for example, in tension, in compression, and the transverse one. It's not so clear on the transverse one, but on the axial one, it's very clear. So this is again some illustration of what the type of campaign that we can evaluate. So for configuration, we always solve the pristine coupon and the coupon with the gap. So it means for each configuration, we will again compute a knockdown factor. So here, what I have done is again, here it's a simple illustration. So here we use IS48552 material, and we consider different type of layup. So the quasi-isotropic, the softer layup, and the hard layup. And here I have considered that I put some gaps in all ply. So every ply I have defined a gap, and I want to see what's the knockdown factor in this case. But here in this configuration, I just insert some ply, some gaps, sorry, on the ply that are oriented at 40, 45 and minus 45. So it means that the ply at 90 at 0 are unchanged. And in this case, I can also evaluate the effect of the gap. Okay, so we are running a bit late. It's already 5. So I will conclude this presentation. So what I have shown you, it's the possibility to compute virtual allowable by taking into account effect of defect. And now it's based on an advanced failure model for the continuous fiber reinforced polymer. So the prediction of the coupon strength is done with Digimat VA. So we have seen the workflow. We have seen how we define the material, how we execute test matrix. Digimat VA contains 2019.1 contains 2 major features. The first one is an accurate material model, and we have seen that we have now good correlation for several aeronautics grade and several layup for the unnotched tension compression, open hole tension compression. And that also gives the possibility to explore the design space to consider any type of layup for material screening, for layup configuration consideration. The second major feature is the possibility to introduce a defect in the coupon. So here we have the possibility to take into account the defect in the coupon and to compute a knockdown factor on the coupon strength. So we solve the coupon without the defect, we solve the coupon with the defect, and then we compare the strength. So this allows also to refine the current method used to estimate the effect of this defect at the coupon level. So it's a refinement on the way we compute this knockdown factor. So just to finish that, we are here to assist you, to help you who are interested to initiate an activity on virtual testing. So that's things that we can support with you. We can help for the material data collection, for the material model definition, because new material model means also sometimes new material data. So that's something we can help to do. And also, we have seen that it's important that we can assist you to define the best practice in terms of coupon modeling. Okay, and I just have to thank you for your attention. I hope you enjoyed the webinar, and if you have any question, I will try to answer right now, or in this case, we can answer also by mail and come back to you with the answer.
Thank you very much, Anthony, for the presentation, and we are really sorry we were running late, but I hope it was really useful, and you can make use of it. We have received many, many, many good questions, and I'm afraid I'm not be able to read all of them. However, we are going to send you an email within the next 2 or 3 days maximum. One of our experts will answer your questions, which I have just saved to your email address. So you will be able to iterate on that, and then you will receive your answer, I promise, to every one of you. And thank you very much for attending, and I wish everybody to stay safe and enjoy the rest of your day, or good night for you. And if you have any other questions, then we are very happy to answer to you. Just one point I would like to invite you for. We are going to organize our global users meeting about ICME, which is Integrated Computational Material Engineering, in Seville in the first week of October. So you will hear shortly about it a bit more. We are watching right now closely the situation, what is going to happen, and then act. But as of today, we think that beginning of October should be fine. So you are cordially invited to join us, join our community, and then learn a lot about how other users are using Digimat or Material Center for their everyday challenges. So thank you very much for everyone, and look out for our emails. We will send you the answer for your questions, and thank you very much for attending. And goodbye for everyone. Thank you for your presentation, Anthony.
Yeah. Thank you. Thank you all.
Bye-bye.
Bye-bye.